Hi everyone, my name is Yusuf and I'm a senior software engineer at CrowdStrike. Today I will be discussing our real-time analytics capabilities and the challenges that we have overcome to achieve them. At CrowdStrike, we are passionate about providing cutting-edge cybersecurity solutions that help our customers to stay one step ahead of the threats. Our real-time analytics capabilities are a critical component of this mission by enabling us to detect and respond to threats in real time. I have been working on our data infrastructure group as senior software engineer, where real-time analytics service is a critical component of our analytical services. In this presentation, I will be sharing some of the lessons we have learned from our experience with Pinot. I will cover our use cases and design choices we have used to achieve our goals. Let's take a look at the two important use cases for our real-time analytics service. First one is system load protection, and the other one is security analytics. Let's start with business problem of system load protection use case. We have tens of microservices that are listening events from a main Kafka topic. While some of those services are handling front-end requests, which requires high throughput, and the other services are working to build some context over the events, which takes more time to complete each request. All of those services are running under strict SLAs and SLOs. So the problem here is event volume on the Kafka topic fluctuates during the day due to various reasons. This can be either expected or unexpected. For example, when a new customer gets onboarded, event volume increases expected or due to malicious activity on certain endpoints, like that increase is also expected. So our agent may report more events. Those events are all related to system performance and resource utilizations, such as CPU, memory, disk, or network. On the other hand, when those events are false positives, this creates unnecessary stress over the services. So each service has a mitigation plan for such situation, but identifying the unnecessary load needs a specialized service. Event volume is tracked continuously and fed into a Pinot real-time table. When increased amount of data volume detected, an event gets published to database. Currently, there is a rule-based system that triggers this event. This event is treated as a signal for increasing load by downstream services. So each downstream service takes actions depending on their mitigation plan to keep their SLAs. The second use case that I want to talk about is security analytics. We are still on the same main data bus, Kafka topic, with the previous use case. This time, events are generated by other downstream services. So we aggregate data egress events from multiple sources into single feed, which can contain duplicate events due to various reasons. We use real-time table with deduplication configuration to ensure that we are only processing unique events. We use our real-time analytics service to provide a more interactive user experience for visualization of data egress events. This allows users to quickly identify potential security threats and take action to prevent a breach. For example, security analysts can navigate to the interactive dashboard for any dimension and create visualization for data egress patterns, top destinations, or top sources, or anything is relevant to the problem. This enables security analysts to quickly identify a malicious user who is going to who is doing data exfiltration to an unapproved destination by the organization. We are using Pinot to detect such unusual activity in our production environment. As we build our real-time analytics system, we have encountered several challenges that we need to overcome. I'm going to mention about three initial challenges that when we have started with this service. So let's take a look at it. One of the biggest challenges is the complexity of our protobuf schema, which includes rich definitions with nested types, enumerations, as well as frequent schema evolution across the environments. On specific parts of the protobuf definition, there are even wrapper types which encapsulates company-specific ontology, which is part of the completely different encoding. So this complexity made it difficult to manage and maintain our schema, especially when it comes to parsing the fields and making changes. The complexity of the schema also had a performance impact, as it requires more processing power to handle the nested types and enumerations. Moreover, in most cases, full deserialization of the event is not required. The other thing is, every protobuf update requires a Pinot server restart, as protobuf descriptors had to be updated. This adds an extra layer of complexity and unnecessary restarts for our multi-tenant Pinot cluster. To address these concerns, we introduced the preprocessor layer as shown in the diagram. It handles complex event parsing and outputs a lean event. The schema of the lean event is tailor-made for the schema of the Pinot table. Preprocessing layer is generating lean event in JSON format that does not require any descriptors to be parsed by Pinot consumers, so no restarts are required. By handling complex event parsing in a separate layer, we had three main benefits. First one is, we have simplified the event processing pipeline and reduced the complexity of our schema. Number two is, we have improved the performance. So consume proto event is partially deserialized, and we are able to skip unnecessary cost of deserialization of large object. Thus, we have formed a lean object in this layer. By outputting a lean event, we introduce the amount of data that needs to be processed by Pinot consumers. This leads to improving performance and reducing the ingestion latency. So the benefit number three is, we have increased our flexibility. So the processor layer provides a flexible way to handle schema changes, allowing us to make changes to schema without impacting the rest of the system. By having the preprocessor layer, we have even unlocked more use cases that require minimal manipulation in the raw event schema, such as creating sessions out of a stream, something like start time and end time manipulation with upserts. However, this solution, of course, comes with a trade-off. By introducing a preprocessor layer, we are duplicating the Kafka event footprint, which can lead to increased storage costs and potentially impact Kafka performance. So we compare the costs and benefits and decide to keep this as a part of our design. Let's move to our next challenge, dynamic Kafka addressing. Another challenge we have faced was our dynamic Kafka infrastructure, where broker addresses can change without notice. This is a constraint in our infrastructure that we had to mitigate. So this dynamic nature had a significant impact on our system, which is risk of lagging behind. If our system was unable to update its broker list as soon as the change is detected, we are risking simply lagging behind the latest changes in the Kafka infrastructure, which could potentially lead to stoppage of the ingestion, so delayed processing of the data. In such real-time solution, simply lagging behind is not acceptable, so we need a solution here. When dynamic address resolution is the problem, DNS record is the most straightforward solution, but in this case, DNS record is not the right answer here due to certain security measures. So our solution here is simply automated broker list updates. To mitigate the dynamic nature of our Kafka infrastructure, we have implemented an automated system that updates our broker list in real time. This system allows us to automatically detect changes in broker addresses and update the relevant table configurations accordingly. And by updating our broker list in real time, we can maintain a stable connection to Kafka cluster and ensure our system is always able to process data in real time. As a byproduct of this solution, We have a table provisioning infrastructure. It keeps the configuration always aligned with the latest release. So this prevents unintended table configuration changes to live longer on production environments. Last but not least, we face the challenge of creating a continuous data feed from Pinot. Single query works fast. This is great. But on certain cases, we need more than a single query execution to better understand the trend. So this is mission critical when downstream services expects a real-time output with a context. So let's think of an example. There is a real-time table and it is consuming events from Kafka topic. Downstream services needs a signal if event volume exceeds a certain threshold on certain window. Tens of microservices can run queries on that Pinot table out of their hundreds of replicas or sometimes thousands of replicas. But this is not a wise way to spend the processing budget. So to address the need of data feed from Pinot, we implemented a system that transforms point-in-time queries into continuous data streams. This system allows us three things. Number one is we minimize the redundant execution of the same query, so increase the efficiency. Number two is provide a continuous data feed and enhance the user experience. Most of the time, these are the service users, but increase the user experience of our service. And number three is ability to build a context over the feed and decide whether to trigger an event or not. Now that we have discussed the use cases and challenges of our real-time analytics service, let's take a step back and look at the high-level design of this service. Our real-time analytics service consists of four main components. First one is, of course, data sources. We have multiple data sources, including Kafka topics, as well as batch data sources that feed data into our system. Number two is processing layer. This is the layer that we discussed earlier as challenge number one, where we handle complex event parsing and output the lean event that is consumed by the Pinot cluster. Number three is Pinot cluster itself. Simply, the Pinot cluster is sitting at the core of this service and storing and serving the data that is processed by the processing layer. So the component number three is data consumers. This is the layer that we have discussed earlier as challenge number three, where we transform point-in-time queries into continuous data streams and provide the continuous data feed to our services. So let's take a look at how those components interact with each other. So the journey of data starts at the source. This is Kafka topic. This is Kafka for our case. Processing layer consumes Kafka topic and handles the complex event parsing task. Depending on the requirements of use case, it performs some data manipulation as well. Output of preprocessor is the lean event. So this is in JSON format, and the schema of the lean event is tightly coupled to the Pinot table schema. So the next step in the flow is Pinot cluster. Real-time table consumes the lean event and performs its internal processing steps. We also use offline tables to store pre-aggregated data, which allows us to store more relevant data for longer retention periods. Offline tables enables targeted analytical queries and improving overall data analytics capabilities for us. We have self-managed Pinot cluster we have self-managed Pinot cluster with multi-tenant setup. So we are not using tenant isolation on low traffic and low volume tables. On certain clusters, Pinot servers are provisioned for single tenant. The last bit is consumers of the data that we ingested into tables. The data consumers can use Pinot tables directly via broker. We have the query scheduler component here as well. It is only relevant for certain tables that requires continuous data feed from Pinot. So this is the design that we are able to handle custom needs of every use case so far. With that being said, I would like to share some observations out of our deployment landscape. We are able to handle 120,000 events per second for a single replica of a single table. This is observed in one of our production deployments. We have ingested over 5 billion events for a single table, and the peak rate of queries per second that we have observed is 25,000 for our busiest table. Our operation at scale involves 5 different production environments globally, and we have over 10 Pinot clusters. Each of them are handling pretty large volume of data and pretty large volume of queries. In conclusion, our real-time analytics system is designed to handle high-performance workloads and provide blazing fast results. We have discussed the challenges we have faced, including protobuf schema complexity, dynamic Kafka addressing, and creating a continuous data feed from Pinot. And I have also shared our solutions to these problems, including preprocessor layer, automated broker list updates, and the query scheduler. Thank you for your attention.